Okay, we have two blocks here. This one 351 4-inch stroke, and this one here at 351 standard stroke has been run for a whole lot, so we will measure how much it will resist and see how much it takes to break it or to take it to turn. 50 foot-pounds of torque, and we will see when we take it. $31.3. Is that correct? Yeah, 31.3. So let's take this and put it on this race block with 0 miles. But what happened here, it's been assembled with heavy duty grease, as you can see. Now let's see how this one rotates. 15 pounds. Let's try again. Even less. 12.8. Let's try again. 12.2. So about 12 pounds. Okay? So that's what we're looking at when we drag rotate these engines. This one's got low tension rings and all that, a lot more stroke, and this one's standard stroke 351 with some high compression piston. Definitely it's not high dollar, but it's basically what we call this, budget buildup. All right, and it took about 30 pounds to rotate. That took about 12 pounds to rotate. Did you see where the power comes in? Subscribe, like, and share. Hi, this is Ben. Good morning, good day, good evening. Anyway, today we will talk about building a healthy street engine. Basically, we'll focus on the short block. There are many videos out there saying this is the best manifold, this is the best cylinder head to use, but I hardly see anybody pay and go through the details of trying to build a better short block. Everybody does this. Heads, camshaft, but let's focus on the block. Now, think about this. The foundation for any engine to make, harness, and produce the power is basically dependent on the ability of the block to seal the compression and the combustion after effects. Without that basic building block, without the basic fundamental requirement, you will have hardly anything. The power will be subpar. So let's start. Now, it's important that you have a very good machine shop. All right, and I get a lot of blocks from a customer or whichever one, and they bring me the block and I don't know who did the machine work. First thing that I could do, just to make it clear, is that I pre-gap the rings and I see what, let's just say we take number 1, and I put the piston in there and see what the gap is. Let's say for a given number, 18 thousandths. Then I go to the next bore and see where the gap is also. It better be close to 18 thousandths. I'll be right on point. But if you see you pre-gap number 1, and let's say it's 21, and you go to second, it's 25, and you go to the third one, it's 26 or whatever, I kick that out. That tells me that whole doggone short block is all over the place. Maybe the guy is a rookie machinist, or they just don't care, but it does happen. So that's one foundation that you do. Check your ring and gap. Start with number 1 and go through all of them. It better be close. If you have an engine that you just got back from the machine shop, or perhaps an engine that you took apart and you have no micrometer, no bore gauge, here's what you do to check the kind of work that's been done on this block. You get your new set of rings, you put it on the bore like this, and you use the old piston as a squaring tool, or your new piston, you put on the top groove or the second groove, whichever way, and you put it down, you go like this. And then you measure the ring and gap. Whatever it says right there, let's say this is a tight 24, I put it in here, and do the same thing. That's squared off. That's a tight 24. If, let's say, you go to the next one, or really this one jumps up to 26 or 28, and it's a fresh block, you better take it back, or you better get a new block. All right? Because when you have 24 in the first one, then suddenly jump to 20, 28 or 30 here, you got a 4,000 bore wear there, and you haven't even started yet. So make sure you check all of them, just to make sure that the bore machine work is really good. Also, when you have, and we've been through this a lot, we get a lot of rings sitting on the shelf, we don't know what they are, and sometimes they're all mixed up. How can you tell the top ring from the second ring? Do this. Okay? That I feel is harder. This usually is the top ring. The softer one's the second ring. And the chamfer usually is on the bottom of the second ring if there's a dot. Some of the top ring don't have a dot, this one has. And usually there's a chamfer on the very top of that. If it doesn't, some of them don't have a dot on the top and it's just square, but usually you'll see a bevel right there. All right? That signifies a compression ring. Even just by holding it, I can really tell which is which. That's good practice. Do this with a used block, or you have a block out there sitting, do that. They'll tell you something. Okay, so that is a very good thing to look for. Secondly, pistons. Now, we're not talking about racing here, okay? And I've said in other videos before, people are building their engines with too low of a compression. Okay, if you have a 306, let me see here. If you have a 306, this is a 9-to-1 flat top kit black. All right, I think part number 115. It's a good piston, but to tell you the truth, for street duty, even for the most modest combination, probably if you don't care about high performance, sure, use this. A flat top on a 347 gets about 10.5 compression. Now on a 306, this is a 9-to-1. So what I suggest is you run the same basic budget, we're not talking about racing here, street piston, which is this. Kit black, it's got a dome on it. You can see that the dome is obvious on there. All right, you can see that right there. And the other one's flat top. Well, let's put it in proper position here. That has a dome. This is about 11.5 to 1, or 11 to 1, depends on the cylinder head you have. This will net you possibly 20 to 30 horsepower, depends on your basic combination. All right, so put a little dominant, don't be afraid, on a street car. Now, when you do that, second concern is what kind of ring pack does it have. Molly, Ross, this guy's here, Kid Black, since it's a budget piston, they have like a 1/16 top ring. Molly, Ross, they have them 0.43 or 1 millimeter. Remember, the thinner ring produces less drag on the cylinder wall, hence a lot of your internal losses. Now, the only drawback to a thin ring is that since the ring is in close contact with the cylinder wall, the heat emanating from the combustion process reflects on the top of the piston, and the path to the water jacket from the piston to the water jacket is through the rings. The thinner ring has a smaller contact point to transfer the heat, so there's a possibility that the top of your piston will run a little hotter with thinner rings. All those coatings, combustion coatings, I suggest if it's in your budget, even for a mild street car, it gets you better gas mileage besides power, coated piston tops. It's very good and produces the results. Now, when you look at all these things, 75% of an internal loss on an engine is with the rings. That's big. 75%. Think about that. Rings and pistons basically produce about 50% of internal losses on the rotating assembly of an engine block. 50%, that's big. 60% of that is with the oil ring. That's why when I told you guys about modifying the oil ring, like I showed in bending the oil control ring to lessen the tension, it's in one of my videos. This one is even more obvious. This one has one ring, delete the second. This with a modified oil ring. This one here, the farther one, is a complete first and second ring with a non-modified oil ring. Okay, look at how this one pulls. Like I said, I wish I had a fit scale, but here it is. Okay, let's try that again. And here's a modified oil ring and just a top ring. If I can show that anymore. Here it is, as you can see. Top ring, modified oil control ring. Okay, and this one here, like I said, oh god, first, second, unmodified oil control ring. If that doesn't show you the rotational drag any more different, then do not attempt this. Okay, and I will go through why and when can we delete the second ring without any ill effects. Okay, be good. Next segment. When do we know when it's time to try and take off the second ring? I wish I had one that just came out of the engine. You're looking at two pistons on the same V8. We did a real rough Mickey Mouse type hone job on the piston on the right, and look at the effects. Blow by way past the top ring to the second ring. Bad. Now look at this thing. The other side was torque plated with a nice hone process applied to the block, and I bet you one side was making power and the other one wasn't. Which one made power? For sure, this one here. This is a good candidate for a second ring delete. But usually you have combustion residue on the top, above the top ring. If the second ring, the distance between the top and second ring is clear like this, there's no combustion residue getting past the top ring to the second ring and getting trapped by the second ring, you can try to eliminate the second ring for less drag. Okay? Because if there's hardly anything getting past the top ring, called blow by to this area on the second, above the second ring, and there is no blow by, then what is this doing? But remember, the second ring is a oil control ring. It is not a compression ring. Therefore, when it's very clear, go ahead and do it. That is a quick way of evaluating if you can get away with it. But if you took the pistons out of the engine, let's say it was running, and you have a combustion, you can see like discoloration here, very dark discoloration, that means you got issues with the top control ring, trying to retain the compression. Then taking off the second ring might not help you at all. But if it's this clean, and I've seen it just like that, well, all bets are off. Try it. Okay? So that's one trick. And like I showed you on this video, what is the ring drag and how significant it is to the whole rotational resistance to the engine. That much heavier. All right? That much heavier. And this one here, so much light. Here it is. Okay, just the oil ring. And what I have here, I will show you how I modify that thing. Okay. Let me look at this. And well, a little bit of oil here, kind of slippery. Here's what I did, so you can see the ends right here. I bent that one there. Okay, and let me pull this one. Let's see how it looks like to you guys. Even pulling it, you can see how hard it is. So you could see that it's got WD-40 in there, so I don't scratch the cylinder wall. See the ends right there? Okay, I haven't bent this one yet. All right, whereas this one, you can decrease the tension some more by bending that some more, a little bit farther back. So there you go. You can see both sides, how the ends are bent. Okay? Here we go. This oil control ring is modified this way, okay? The ends here come in this configuration, and what we're going to do is we'll bend the corners flat like this so they sit flush, okay? And that will reduce the tension. And it's kind of hard doing this because I usually do this by hand without looking at the camera. Okay, notice that right now that is now straight. One side is vertical. Okay, now we'll do the other side. Slowly again, have patience. Remember, this is spring steel, so it snaps back to its old position. Okay, now there you go. Now there you go. Now you see it. Now they're flush. Okay, it's not an A configuration anymore. And what it does is it brings them closer to each other, reducing the radial tension of the oil control ring. Okay guys, I hope that's clear. Whereas this one, after I bent it, it's flush side to side. Okay, the V tension there creates a lot of spring outward pressure. That's why it drags on the cylinder work quite a bit more. That will drop your loss from the ring drag significantly. It might have dropped you 40%, 30%, whatever you do decide to how much you want to loosen it up. Also, don't do this. Do not run connecting rods with pin oilers on the piston, because that will throw unneeded oil around the cylinder walls, especially when you modify your oil ring. This oil control rings with additional oil being thrown by the connecting rod oiler to the piston pin just puts too much windage all around the whole rotating assembly. Again, a net power loss. If your connecting rod came with this oil hole, use the bearing that comes covered. There are rod bearings out there that has a hole in the upper half. Avoid using those. Here's a picture of it. There's the square hole, and that shoots directly to the piston pin or the bottom of the piston. That's a no-no. Do not use that. Just use a solid upper main bearing shell. Now, ring temperatures, 600 degrees on the top ring. That's basically representative. The second ring is about half that, 300 degrees Fahrenheit. And the coldest among the ring pack is the oil ring, of course, is the farthest away from the combustion heat. It's at, I think, 250 degrees Fahrenheit. That is great, but the problem there is that's where carbon and sludge starts to develop. Now, I've seen a lot of oil control rings, they exhibit a lot of carbon buildup there. Then they actually freeze in their groove and they don't do their job. And then you have your oil consumption issues, oil control issues. Remember, any oil that gets inside the combustion chamber, it will turn to carbon. That carbon will glow. That will create pre-ignition sources. And most of all, when there's oil inside the combustion chamber or present in the combustion chamber, it effectively drops the octane rating of the fuel being used. So be careful, especially in boosted condition. But we're talking straight here. You don't want an oil-consuming engine, most of all. When you install pistons or piston rings, make sure you use one of these. All right. Do not spiral the ring like a lot of old-timers do. Put one end and spiral it around. Don't do that. You can damage the ring, especially those thin rings. Use one of these ring pliers. It's a must-have. Okay. Don't just. You gotta have the proper tools in order for you to assemble correctly. We can do all sorts of Mickey Mouse engineering stuff, spiraling it. Except if you're very good, then maybe you've been very lucky. But there are instances where it'll come around and bite you. Just use the proper tool for the job that needs to be done. Now, valve train. It is important. For me today, I will not, remember that, I will not build an engine with a flat tappet camshaft. The flat tappet does not lend itself to today's basic oils. Very thin. And the flat tappet, when it's on a lifter bore, is offset to one side. And while the cam is turning, it's rotating. When it's rotating, that keeps it alive because the oil surface gets transferred all around and takes the heat out of the frictional part or the rubbing part of the cam to the lifter itself. So rotation is very important. The very thin and very slippery synthetic oils today doesn't exhibit that. I mean, there are good lubrication properties, but some of them are too slippery. And when the lifter stops rotating, cam goes round. When you have a roller cam, it's important that with the wheel, you can just about use any kind of oil that's sold out there. With a flat tappet, you gotta be very careful and also, when I use, or somebody insists on a flat tappet, I use diesel oil, Dela 400, Motorcraft to break in, Motorcraft diesel oil, it's not synthetic. I use diesel oil for a flat tappet combination. In fact, I just had one here come in, 348 49 series Impala, Chevy Impala, and the cam went round because they built it with a flat tappet. And I told the owner, just gotta update it. You gotta put a rotor camshaft in there, so it'll be no issue whatsoever. It's sad when the guy spends so much time and money, the block is finally detailed, everything, he puts it in, and then it fires up, it's backfiring on the carburetor. An indication of a, round exhaust lobe. It's not letting exhaust out and just backfiring through the intake, or a round intake lobe. Could be just that simple as well, right? But it's never good. With today's oils, they're superior than what we ran 25, 30 years ago. I run a stock pump. You don't need those high volume 80, 100 PSI oil pump. Not needed at all. Any added pressure takes added horsepower to turn that oil pump. Avoid that. When you run today's thin oils, even if you're running a 2050 synthetic or 1530, 1540, whatever synthetic, they protect the bearings much, much better than the old oils that was sold 20, 25 years ago. Today, all the synthetics are superior. Okay, and it's very important that you employ a stock oil pump. It takes less to turn, and the protection is even better. Now, I've dealt with some friends of mine here in Vegas. They were looking at one Japanese engine, and they were putting in 100 pounds, 125 pounds of oil pressure to keep their doggone turbocharged Japanese engines alive. And I looked at both of those engine combinations. One was a very successful 6-cylinder. The main galley is big enough to support bringing a lot of volume into the bearings. Now, this particular engine, the oil galley was half of what the other engine had. And I see them, they put restrictors on, the top end, all these things, and they still run 100 pounds of pressure. That means they still haven't fixed anything. It's not even a band-aid, it's bad design. So what I suggested to these two friends of mine is they went with external, they plumb it to the front of the block through the oil pump. 3 lines, braided hose that feed near the last number 5 bearing, 4 and 3, with an external braided hose. Oiling directly to the last 3 main bearing areas. And from what we can see right now, the pressure could be dropped because, come on, 100 PSI for a racing 6-cylinder, even a 6-cylinder, that's a hot street type thing, serious street build, there's no use for that. And when I saw the problem, I said, run an external line. You gotta feed the 3 main bearings on the back, which was too far because the main well started the first 3 main bearings, then got even smaller. So by the time it gets to the rear, it's too little, too late in the game. So I suggest that an external line would definitely help. The sample I showed at the start of this video was an engine that I rotated and it only cranked with 31 foot-pounds of resistance, 31 foot-pounds of torque resistance or rotational resistance. When I actually opened that engine up, it was worse than I thought. Because when I saw 31, I go, okay, guy did a good job. But when I finally got to the bottom end, took all the pistons and rings out, 3 of the rings actually collapsed, the top ring. That's why the rotational resistance was, looked good. But actually the owner told me that he had a dead misfire on the engine, of course. The top ring were dead in 3 cylinders. And then it would have come back to, you know, between 40, 45 foot-pounds of rotational resistance. A far cry from what the engines see here. Even with grease in this race block, assembly grease on the bearing, it still managed 12.2 of rotational resistance. Usually if I use engine oil, not the kind of assembly grease, it'll probably read about 7.5 to 8 foot-pounds. That's significant. You don't have to fight that rotational resistance even when the engine's running. And then to top it off is that the 351, or the stock engine, had a 3.5-inch stroke stock, and the race block had a 4-inch stroke. So in essence, if that race block had a 3.5-inch stroke, it'll resist even less than the stock block. It will be no comparison. Imagine you have an engine that's taking 20 foot-pounds of torque or more to turn, more than what the other one is doing. That's 3 horsepower. Okay, we have 2 blocks here. This one 351, 4-inch stroke, and this one here at 351 standard stroke has been run for a whole lot, so we will measure how much it will resist and see how much it takes to break it or to take it to turn. 50 foot-pounds of torque, and we will see when we take it. $31.3. Is that correct? Yeah, 31.3. So let's take this and put it on this race block with 0 miles. But what happened here, it's been assembled with heavy duty grease, as you can see. Now let's see how this one rotates. 15 pounds. Let's try again. Even less. 12.8. Let's try again. 12.2. So about 12 pounds. Okay, so that's what we're looking at when we drag rotate these engines. This one's got low tension rings and all that, a lot more stroke, and this one's standard stroke 351 with some high compression piston. Definitely it's not high dollar, but it's basically what we call this, budget buildup. All right, and it took about 30 pounds to rotate. That took about 12 pounds to rotate. Did you see where the power comes in? Also, as a budget combination, do not be afraid to turn down your stock crankshaft on your Fords or Chevy. They're plentiful at the junkyard. Just like people buy junkyard LS and put camshaft in them and maybe some valve spring and they turbocharge it. Same thing with the Fords. They're all over the place. Crankshafts are cheap, and I knock them down 30 thousandths or 10, 20, 30. Don't be afraid. Knock it down 30. Rotational resistance cut down. All right. And there are some bearings out there from Mexico, which is called Clemex. And I said this on the other video, is a Mexican version of Clevite bearings. In fact, the part number are the same. But they all go all the way down to 40 over. Now think about, by the time you deleted your second ring, and then you you modified your oil control ring, and then you knock down your rod bearing diameters, rod and main. Every little bit helps. Taken as a whole, this is an advantage. A lot of people will not, mind the details. Oh, that's very little here. Oh, don't worry about that, that's very little there. Ah, that's a waste of time. All those help. Taken as a whole, when you combine all of it, that's a big jump. People that don't sweat the details end up not winning any races, or they'll just run okay. Okay, here's a quick test to see if you have a good crank. The one on the right, of course, is a cheap, I shouldn't say lower quality, but the Ford cranks are from the factory are pretty doggone good. All right, they can take a lot of punishment and make a lot of power without breaking. And the one over here is a scat forging. Now, how do you test these things? If, let's say, this tool has been sitting on your garage or your buddy's garage, he's got a bunch of cranks, you line them up and do this test. Okay, the stock one, it's obvious it's rusted. The forging will never rust as much as that one there. All right, under the same circumstances. But here's a quick test. Here's the sound that a stock crankshaft will emit when you tap it. Here's the sound of a forging aftermarket. Okay, that's a quick way, just like washing the block, and see who rusts first. That'll tell you. Pay attention to all of them. Like I said, if you have a 430 bore, if you have the budget for it, run the bore diameter close to that. All right. The crevice losses, I said. Ring position is important. The higher the ring pack is, the more power you're gonna get. Same thing with the head gasket. If you have you have a 30 over block and your head gasket is 4/100, which I see a lot out there. All right, 4/100 bore. You have a lot of crevice losses around 70 thousandths. Okay, if you have 30,000 and then you have a 4/100 bore diameter, you have a 30 over bore, you have 70 thousandths all the way around of trapped gases, or EGR, safe spaces, if that's what we call it. All right, and they will cut down on your power. So do all that. Stock type oil pump, run synthetic oil. That is significant. That's why when you see somebody with a pretty good running engine, it's got the same basic engine as yours, you start to wonder, what did he do that I did not? How come he's so much faster? It's all in the details. Now, somebody said to me before, what are you wasting so much time in running a light crank or lightweight aluminum rods? But just side talk about racing. I think it's good enough. You don't have to spend that extra money for a little bit more or less weight. And I tell them, well, I like to run a light crank for a full race application, light rods, light pistons. Why? I said, let's put it this way. If you and I have the same amount of leg power or horsepower in our legs, I put sneakers on, running shoes, and I have your combat boots, which is like a heavy crank and run. And we run a 100-yard dash or even 50-yard dash. We make the same amount of leg power. I will beat you, I guarantee you. The potential to make power is the same, but what's strapping you down is the added weight. I'm running on sneakers, you're running on combat boots. See if you believe that weight doesn't matter. It does. Please subscribe, like, and share. Good morning, good day, good evening from whatever part of the world you're tuning in from. Welcome again to my channel. Please subscribe, like, and share so we can keep this going. Anyway, here we go. I've been getting a lot of comments from the last video about low dollar valve train mods on a 5-liter or 351 Windsor engine combinations. But a lot of them are asking also, how do you properly adjust the valves, or how do you adjust the valves correctly? Well, what may be correct for me might be wrong for somebody else. But here I will do a slow breakdown on why I adjust it this way. Years ago, a friend of mine is out there in Willow Springs with a 914. He was really running, and I can hear the valve train clatter. And I watched him adjust his valves, and I'm going, is that how you adjust your valves? He goes, yeah. So I told him this process that I'm doing, and by the time we were done, the clattering is significantly reduced, and he had more power. And I see it all the time. I see people try to adjust their engines on the compression stroke, so they think they work, until you have a degreed dampener with the cylinders stating it's on compression. If you don't have that degreed, it's a stab in the dark. You don't know if, especially with 16-volt system, high torque starter, you think you're on compression, but you're already at the onset of the valve opening starting to come up on the ramp. And then when you're adjusting it, you think you're really doing it correctly, but it's wrong. At the same time, I see a lot of people try to adjust. They're actually on overlap when both valves are, one is intake valve is closing, exhaust is opening, and they ended up leveling, and they look like they're on compression, but they're not. Okay, so we'll touch this and see what you think. I hope it helps. Here we go. Okay, this process is called ICEO, intake closing, exhaust opening. When you say IC, intake closing, watching this intake valve right here, when it starts to come up and close, you adjust the exhaust. When the exhaust on ICEO, when the exhaust kicks open, you adjust the intake. That's the only way you can do this correctly. You don't want to do this on compression because there's just too much going on. Here we go. Oxycone, rotating the engine. Exhaust started to open right off the bat. Now we can adjust the intake. So when we're looking at the block with the lifters in place, once its exhaust lifter starts to open, look at where your cam pin location is at, almost 9 o'clock. We will look at the camshaft for the lifters are in position. Now when you see that it's almost at 9 o'clock position and it's turning clockwise, here's the lifter, exhaust lifter location at. Here's where it is. It just went through the flat section, it's climbing up and starting to kick up right here. Okay? When it started to kick up right there, look at what the position of the intake lobe is at. It's right about there. There's the intake lobe. On the very opposite end, right there. Okay? So you put that almost 9 o'clock, and your intake valve is here, positioned at the base circle. Or intake lifter, it's positioned at the base circle. There's the lobe, guys. Okay? So, anytime the exhaust starts to open up, traveling here, it starts to hit the ramp, it starts to lift up, and that is at about 9 o'clock, almost 9 o'clock. Intake lobe is on the other end. Okay? That's the best explanation I could do for everyone. Here we go. Let's start the process. Turning the engine, exhaust kicked over on the get-go. So what we do is you go like this. The exhaust valve opens up real quick, and on a hydraulic roller, you go like this, or you fill the push rod. When it stops, okay, you'll feel it tighten up. When it starts resisting on it, while you're turning the pusher, starts resisting or there's no up and down movement, what you got to do now is do this. 12 o'clock, you go to 1:30, okay? You snug it down, then you turn it to 3 o'clock. That's it. That's simple. Or, when you do that, if it's not a hydraulic cam, you put your feeler gauge and you turn this, and then you lock it the same way you did with this hydraulic cam. All right? This is the time that you lash it with a feeler gauge. All right? Now, I usually do this and I wedge it against the stud, because if you just tighten it up strictly here by closing it up and tightening it, well, sometimes that has a chance to loosen up. So like I said, here we go again. Now, since we did the IC intake closing, okay, now let's start. We will look at, since we did the exhaust opening, exhaust now maxing out. Now the intake, see that? Intake valve starts to come down and it'll start to close up. And when I said intake is about to close, which is now, look at the position of the pin. 330. The lifter just came up from the peak lift, starting to close right here. Correct? And I said, when the intake starts to close, which is at this position, guess where the exhaust lobe is at? Right there, on the other side. It's hitting right here. Right? That's where it's hitting. Could you see that? ICEO. Intake starts to close. Right there. Exhaust lobe, which the peak is right there, and exhaust lobe is on the base circle. All right? I hope that's clear. I hope that's clear. That's why I do ICEO. I cannot show that inside the block. It's hard to see. Intake valve starts to come down and it'll start to close up. There you go. Now you adjust the exhaust. Here we go. Again, you start going like this. Up and down, clicking. Now the line, that's, and you can feel the push rod start to tighten up. That's zero lash. 12 o'clock. I go to 1:30. I snug it down a little bit, not too tight, and I wedge it against. There we go. There we go. 3 o'clock. All right. I think that's clear. And again, at that point in time, use your feeler gauge and do the same thing here. All right, with the proper clearance. You don't have to really wedge it against because you're probably damaged, but I doubt it. The stud and this adjuster, but just a little snug, and then you go to 3 o'clock from 1:30. Or if you want to do a half a turn, do it over here, and then turn it till you get to about this way, snug it, then proceed to turn it to half a turn. I hope this video made it clear why we go about this way of adjusting, and I think it takes the confusion out of the whole process, that we are actually doing it more accurately. What might be, like I said, right for me might be wrong for somebody else, and what's wrong for them probably not the right way, and they still keep doing it. It's okay if you're close, but sometimes flow is not good enough. In this high level engines that we have today, lots of horsepower, you gotta be on point. You gotta do it accurately. The margin of error, especially with high horsepower, high RPM engine, becomes progressively narrower. When you have a low performance engine, your margin of error is very wide. When you have lots of RPM, lots of horsepower, that's like a pyramid. The more higher you get up on the horsepower curve, the less margin you have in ignition, air fuel requirements, valve train adjustment. There's just so many things that may go wrong. I hope this he's well with everybody else. Thank you.